Right. So flow-based models, they use a different way of thinking, different paradigm. Okay, and they're a very peculiar class of models. So we will start with a very, very simple example. Okay, so let's say that we have a random variable that is normally distributed, and this is a standard normal. So we have mean 0 and variance 1. And now let's say that we transform this random variable and we will multiply it by 0.75 and we will add 1. And you know, it is not an image, it is nothing, it's just one single random variable, but you will see that there is some very interesting rule behind how to calculate distribution for that. And for instance, question is, what is the PDF, so probability distribution function for u, for this new random variable? And I can give you straight away what is the answer. So the answer is, this is again a Gaussian, but with mean 1 and variance 0.75 squared. And this is the blue one is the standard Gaussian, and this is the new distribution, right? Right. You can say, all right, I see something, I see a pattern. We add 1, so we have 1. We multiply, let's say scale this distribution, so we will have the variance here. This is, of course, a good way of thinking. It's like reverse engineering. But of course, we should know what is the principled way of calculating that. And the principled way of calculating that is given by the change of variables formula. And this tells us that if we have a distribution of P of u, we can, and we have a transformation f. If this transformation is invertible, we can actually calculate the new distribution by taking P of f inverted of u, and then calculating the absolute value of the determinant of the Jacobian matrix. So this is called Jacobian. We'll talk about it in a second, but this is just derivative in this case of inverted function f with respect to u. Okay. And if we take our example, so we can say that, all right, because f inverted f of u, so if we look here, so it will give us v, right? So that's why we can plug it here. And so in this case, this is u minus 1. This one goes here and divided by 0.75, right? Nothing special. And the derivative of that is simply of this. It's simply 1 divided by 75, 0.75. So it's 4 divided by 3, right? All right. We plug it into the formula. So this is, we plug it into the standard Gaussian definition. And we, after transforming everything, we get the following Gaussian, right? And why we see that this is a Gaussian? Because this is, again, if we recall the definition of Gaussian distribution. So this is exactly, this is 2 pi times variance times e to the power of minus and so on, okay? So this is simply the Gaussian, okay? And that's why we can say that this is our final distribution. Whew, all right, so we went through this very simple, boring example, but I hope that you see that this is a principled way of calculating probability distribution functions of some transform variable, random variable. And of course, now we can use it for higher dimensional problems. And again, I stick always to images. I remember in one of the Q&A sessions, you said that you're talking all the time about images. Can we use it for text and so on? We can, but it's easier for visual presentation. It's easier to think of images. So let's say that now we will turn it into a model, or this rule will apply it to images, okay? And so we have, let's say, the multi-dimensional case. We have a vector of pixels, and we just simply apply it to pixels. And where this fellow here it's now, as I told you, this is determinant of Jacobian matrix. And Jacobian matrix is simply a matrix where in each row we have a derivative of a function for given variable. So first, in this first row, we take derivative with respect to first variable and so on. And in each row, we take the first, so the output of the inverted function the first position and so on and so on. All right. So this is how we generalize it to multidimensional cases. And now, how we can utilize this idea for modeling images, for instance, or some interesting objects, right? From AI perspective, of course. So first, we must think of a sequence of, or in general, of invertible transformations. So here a sequence is not an accident, because of course we can think of neural networks. So applying sequentially some invertible layers of neural networks. And we can also think of some simple distribution, like for instance Gaussian. So this is, in other words, or maybe this is a nice interpretation of this change of variables. So in general, the change of variables is that, for instance, we have a Gaussian distribution, so it's something like simple distribution, and we try to transform it through this f to some fancy distribution, right? It could be even multimodal. So this is the idea. And now we say that we think of some sequence of transformations, and why, of course, neural networks, keep in mind, but of course it will be also, yeah, so it will be something like stage by stage, we just transform it. So we have this example, we have this simple distribution, Gaussian, then we have, you see, we move a little bit like this probability mass to some other place, and at the end we have something like that. What I always like to think about is, let's imagine that we have a pile of sand. So this is a pile of sand, nice sand that is so ideal. And then this transformation f, this is my hand, okay, or my hands. And now we start recording, okay? And so I move like a little bit of this sand, a little bit to the right. So it's, for instance, I take this side and with my hands, I just take a little bit of sand and it's moved here. Then I move a little bit to the left, to the right, and in the end I have a mess, and I have this multimodal distribution, so multiple piles of sand. And because I said that I record it, I can record it, I can play it in reverse, and I can always see how my hands now would move back, so that this nice chaotic distribution, this situation, it's getting more and more like the original, and in the end, of course, I will get the original stack of a pile of sand. And this is exactly what we mean by this transformation. So this is the forward, let's say, pass, the inverse pass, and this is how we can always invert these transformations to get back what was in the very beginning. And of course, now we have multiple steps, so we need to take it into account. So that's why we have this product here of these multiple steps. Okay, but still, this is the change of variables. Here is a very simple example with two moons data sets. So here we have that we in this let's say here it's presented the other way around. So from this very complicated distribution, we transform it to Gaussian, okay, and of course we can then invert it, and from this crazy distribution we can get this simple back. Sorry, this complicated back. So these two moons back. And now since we know precisely how to sample in this simple space, let's say from this simple so-called Bayes distribution, so because it's standard Gaussian, so we need to just sample from this standard Gaussian some points, and by reverting these transformations, we will get some point here, this will go here, this will go here, this will go here, and so on, so on, so on. All right. So this is the general idea. Right. So this is the model. This is again the same formula. So please don't be afraid of this formula. This is just you know how this is expressed mathematically. Okay. So if you have a problem to get what is going on, just go over again a couple of times. And also please remember, I forgot to mention that the Jacobian, actually this is volume. What does it mean? It means that if I have, for instance, a square and I want to transform it to something new, if this simply just, you know, it kicks one side and this is just a little bit shifted, but the volume is the same. So the area of this and this is the same. I don't know, let's say 4. So Jacobian will be simply 1. There is no change of volume. But if I do a square and after this f, I have something like super big. This was 4, this is 16. So then Jacobian will be, of course, appropriately bigger, and in this case, probably it will be 4 or something like that. So this is how we need to rescale our probability distribution so that, of course, this probability must sum to 1, right? If we calculate integral, so it must sum to 1. So of course, this fellow Jacobian, it ensures that after transforming distribution, random variable with f's actually, this whole distribution, this new distribution, this p of x sums to 1, right? So this is what it does, right? And one thing that is important to remember is that for this flexible transformation, surprise, surprise, we use, of course, neural networks, but we need to ensure that they're invertible. So we just cannot take any neural network and that's it, you know, job done. We must formulate a very specific neural network, very specific architecture to be invertible, because otherwise you would have problem to calculate this guy. Because for arbitrary neural network, this could be prohibitively expensive. And yes, so this is what I just said. So we just need to remember to take such neural network, such architecture that we can easily calculate the Jacobian. And in general, this is the main issue in flow-based models. So this is, you know, the research is just going into such direction that how flexible neural network I can pick for which I can still easily calculate the Jacobian. And the first big breakthrough was RealNVP. So it is real valued, I think, non-volume preserving flow, the full name. And the idea was extremely neat and beautiful. So what they proposed, so they proposed to take such transformation that we take our input, okay, let's say, right. We cut it in two. This one we just simply copy, and the other part we transform with some transformation, let's say f. Okay, and we just get these two things. And how we define this transformation f here? It is the following. So first, we just scale with S, okay? Maybe I take different color. We just simply scale X, the remaining part, this part, we scale by this formula, and then we add, so we shift, translate using another part, okay? And now both S and T, they are neural networks and an arbitrary neural network, whatever we wish, okay? And very important thing is that they are this transformation F, I called it F, right? This is simply invertible very easily because what it requires from us, we can start from this part or from this part. So to calculate xd plus 1 to d, we just need to subtract t of x1d. We just go this, and x1d we know because this is simply reverting the order. So we just subtract t, we get minus t, and we just divide. Oops, I see that there is a mistake, of course. It shouldn't be like that. It should be like this. This is element-wise division. This is element-wise multiplication. It should be like that. Okay. So you see that we can easily invert it by design. And this transformation is known as affine coupling layer in literature. All right, so now we have this invertible transformation, we are happy. And now, of course, the question is, what about the Jacobian, right? The guy that gives us this headache. But it turns out that it's actually very, very nice, because here we can even say that this is, I'll make it in color, this is like plus 0 times x d plus 1 to d. So now, because we are multiplying, so here, if we look at only this first row, so this is we calculate gradient, or sorry, derivatives with respect to parameters from x1 to d. So this is simply the identity matrix. So here we have small identity matrix. On the diagonal we have ones, and everywhere else are zeros. Here we have 0. So if we calculate the derivative for this first row, we have ones on the diagonal and zeros. And then for the remaining, so this part and this part, here we have gradient with respect to, or derivatives with respect to first part of the vector inside. And this is pretty complicated because this is neural network, this is an arbitrary neural network. So it will be rather complicated matrix of derivatives, but we don't care about them, because for the second part, where we calculate with respect to xd plus 1 to d, we will simply be left with exp of this neural network inside, okay? And why this is beautiful? Because if we want to calculate determinant of such matrix, remember, this is we don't care about, we don't calculate it for now. Because when we calculate determinant, it is simply the diagonal of this matrix, because here we have zeros, and this is in general triangular matrix. Okay, and for triangular matrices, the determinant of the triangular matrix is just the product of the diagonal, okay, here. So simply what we get, we just get a product of exponents, and since the exponent, the product of exponent is exponent of sums, so we just need to just calculate sum of it, of these scales, right? And since, of course, in the end we get, oh, I didn't mention that, but of course we in the end, we are interested in log likelihood, right? So we have this simple distribution, and we have minus logarithm of determinant Jacobian. And since we know this is so log of this fellow, it's simply a log with x will, oops, sorry, some small technical issues. Right, again. Okay. So we have logarithm of this that Jacobian. So then it will be log with x will cancel out, and we will be left with this. Okay. So this is what we will get as log of the determinant. Right. What is also very nice is that we can introduce the idea of autoregressive modeling here as well, because we can use it for modeling this simple distribution. Okay, we can use this idea for modeling this. And how we can do that? So because we cut it into two pieces, so we can and we apply f, so we can for instance here we can also maybe other way around, I should say, we can model this pi 0, we can model in an autoregressive manner. Okay, and now we can ask ourselves how we can model it in something like in one forward calculations. So we can do it because, again, if we want to calculate, for instance, distribution for z of x3, so we see that by applying these coupling layers, we will model everything, and we will have output of this layer that actually looked at everything so far. Okay, so this is how we can model it in this way. So instead of having here z1 and z2 explicitly, we will take h3, and we can do the same here. We have again coupling layers, and this coupling output of this coupling layer had already access to everything below, and this will be this h4, right, used, and so on. So this is very interesting and important. All right. Moreover, to improve this transformation, so we oops, sorry. So we need to we can do something more, and we can, for instance, use permutations. So what does it mean? It means that we can permute pixels as we wish, because permutation is invertible. Okay, and it helps mixing. We can also divide variables using something that is called checkerboard pattern, right? So it's really like we use this, 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 but we leave out, we don't transform this. So when I said that we actually divide x into two pieces, right? This is left, this is copied, and this is transformed. Actually, we can use it differently. So we can use also such scheme like here. Okay, so we don't use this anymore. We can use this. For images, it could work better. And another thing is something that is called squeezing. So we reshape image because, of course, images are tensors that are 3 channels and height and width. And now it doesn't, this number 3 doesn't fit very well our this scheme that we divide something into two pieces, two parts. So we can reshape it. And we can, for instance, get a different tensor. And this is, for instance, I don't know, something like 6 times new height times new width. Okay, so this is something that now we can divide this into two equal parts. Okay, this tensor, right? This is in a big nutshell, of course, if you are interested in this topic, so just let me know and we can maybe work together on something. And here are generated images and real images. At the first glance, at least for this bedrooms data set, it's almost impossible to say which is which. For faces of people, after a second or two, you see that this is off a bit, this is off, and so on. This is a bit off. So you can see already on which side is real or in some samples. If we generate something even more complicated, like this real images or natural images, how it's called. So you see that, for instance, this model is really off here, 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 here. It's hard to say what is here. So you see that, sorry, on the left we have real and on the right we have sampled. But this was in 2016, ladies and gentlemen, and it was already very powerful, okay? And this was really one of this big, one of the best years for generative modeling, as you can see, that it was really, really amazing. And people were really something like taking their jaws from the ground because it was so great. And then in 2018, there was a paper called Glow, so generating flow. And it was a big model, around 1,000 convolutional layers with learnable one-on-one convolutional instead of permutation matrix, with some specific architecture. I don't want to go into details. Please read on that maybe, because this is the best way to learn about it. But in general, this Glow, it's just a little bit a bigger architecture than RealNVP, bigger model in general, and with some small refinements. But this is more or less the same idea as flow, the same coupling layers and so on. But then their samples were something like really breathtaking, So this all faces, all these faces, they are generated. Okay, you can spot that here is something off, maybe here a little bit, maybe here. If you look at all these pictures, so there is something that you can see that this is artificial, right? But man, this everything is generated, okay, and this is how high quality images. So it was something like really big breakthrough, and such details of face, like here wrinkles somewhere. It's really amazing. Okay. Here are interpolations in the latent space. So for instance, when they went to the Z space, right? And they did the following. So they took an image, like for instance, what's the name, Tyrion, right? And then they went to the latent space Z. They did the same with the other actor. They went to the Z and they started interpolating these Z's, right? So just multiplying by alpha plus 1 minus alpha, and they created the whole path in the latent space. And for some point in this path, they were generating inverting transformations and were generating new images. So you can see as nicely one face is transformed to the other face. Okay, and with female actors, it's even maybe looking a bit better, right? And here the same. And you can see that even if one actor is more showing a left profile and second actor is showing right profile, so you see that all these faces in the middle, they actually start turning. Okay, so this is really remarkable. This is really great score, very interesting. Right. And the last slide, what I would like to highlight is that you can also use flows, normalizing flows, in a combination with other models. Like for instance, there were papers on using normalizing flows for VAEs. And for instance, one idea is that instead of having Gaussian encoder, we can have Gaussian encoder plus some invertible transformations on top of that to get a flow-based encoder. So it was in the paper from Danilo Rezende and Shakir Mohammed in 2015, if I recall. Then together with Rane Vanderberg, Leonard Hasenclever, and Max Welling, we worked on another version we formulated new normalizing flows for encoders. And together with Max, we also propose householder flows. Google people and OpenAI people, they propose inverse autoregressive flows. So all these ideas, they are for making encoders in VAEs more powerful. And also we can use it for modeling the prior in the latent space, right? So in VAEs, and this was the idea in variational lossy autoencoder, again from, I think, OpenAI people. But very recently, with a great student of mine, master student Yannis Katopoulos, we also used RealNVP for the prior and as a small component of a bigger project, but we use it here, and we also got way better scores, way nicer generations. So please remember that these models, they should be, so they could be, sorry, not should be, they could be combined together to get something like more powerful. And that's it. So this is the last lecture on deep generative models. I hope that you enjoyed this, this small, let's say, series of 3 lectures on these topics. If you are interested in these topics, please write me an email, throw me a message, and maybe we can work together or on a master project. In general, I want to say that it is, in my opinion, extremely important topic in deep learning and in AI in general. And if you don't remember why, so please go back to the first lecture in this mini series where I explained that how we really need to model the likelihood of an object in reality, okay? Because we need to get some notion of uncertainty. If some object is likely to happen, so it's fine. It means that I know it from the past. And this is as a standalone approach. This is of course important for generating new examples, right? So if we can also have an approach that will generate fake examples, but that resemble reality. So this is also very, very useful. Thank you very much, and see you during the Q&A session.